In this video, I want to talk about something known as the method of Lagrange multipliers. The premise is that I want to maximize or minimize some function, which we'll call f, but there's more to it than that. There's a side condition or constraint that some equation be true as well. So the general form of such a problem is as follows. Want to minimize or maximize some function f of x, y, and z is subject to the constraint that g of x, y, and z take on some constant value. The thing that I'm trying to maximize or minimize is often called the objective function, while the side condition is often called the constraint equation. Any equation can be written in form some expression equals a constant, so there is no loss of generality by doing this. It's easiest to think about this in terms of three variables, x, y, and z, because we have ways of thinking about what certain things mean to us. A single equation relating x, y, and z, if you'll recall, represents some sort of surface in three-dimensional space. Imagine that I have a point, P, that lies within that surface, and at that point, P, there is no point in the surface close to P where I have a larger function value, so that I have a local constrained maximum point at P. If I draw a curve in surface, g of x, y, z equals constant, that passes through P, if I really have a local maximum within the surface, then we can say something about the gradient of the function itself. The directional derivative along a tangential direction at point P of the function must be zero. Otherwise, the rate of change would either be positive or negative. And as we've seen in the preceding discussion, that precludes the possibility of having a maximum or minimum. Observe, though, if I sit at point P and traveled in a direction out of the surface, I don't care what the directional derivative in that direction is. It's going to be necessary that the directional derivative be zero, but only for tangential directions. For every unit vector with initial point at P, regardless of which direction it is, as long as I have a tangent vector, then the directional derivative must be zero. Assuming our function is differentiable, though, I can use the dot product formula. If I'm to have a constrained maximum or minimum, the dot product of the gradient of f with any tangential direction must be zero. That means that the gradient of f, if it's not zero, has to be at right angles to every tangential direction. So the gradient of f at P has to stick up out of the tangent plane at right angles. On the other hand, my surface is g of x, y, and z equals a constant. Assuming that the gradient of g isn't the zero vector, gradient of g at point P sticks up at right angles to the tangent plane as well. It could be that the gradient of g literally points in the same direction as gradient of f, or it could be that the directions are 180 degrees opposite. In either case, the gradient of f will be some number times the gradient of g. The first order differential conditions to have a constrained maximum or minimum then are that the gradient of f has to be a multiple, which I'll call lambda, times the gradient of the constraint function. It's important to recognize that this just lines the vectors up correctly. I still have to insist that I'm actually in the surface that I'm interested in being in, though. The thing that corresponds to f prime of x equals 0 is gradient of f equals lambda times gradient of g, and g of x, y, and z must be the appropriate value. If you're wondering, there is a second derivative test for this situation, but it would be inappropriate to talk about it at this juncture. As an example of this kind of thing, I'd like to look for candidates for minimums and maximums of the function f of x, y, and z equals x plus 2y plus 3z, but not just any x, y, z will do. I want to insist that only candidates that look like x squared plus y squared plus z squared equals 16 should be considered. I'm going to look at the surface of a sphere, and out of all of those points on that surface, I want to find the candidates for the biggest and smallest value of this function f. The gradient of f is easy enough. F is linear in terms of x, y, and z, so the partial of f with respect to x is 1, with respect to y is 2, and with respect to z is 3. The gradient of g is also easy to get. The derivative of this with respect to x is 2x, with respect to y is 2y, and with respect to z is 2z. Our differential line up the vector condition says that this vector must be a multiple of that vector. So to get a maximum and minimum, it is necessary that this be true, but this doesn't guarantee me that I'm on the surface of the sphere, so I have to throw that in as well. I have a system of two equations, but one of them is a vector equation, and the other one is a scalar equation. It'll be instructive to split this up into the separate pieces. If I look at the first, second, and third components of the vector equation, I'll find out that 2 lambda x must be 1, 2 lambda y must be 2, and 2 lambda z must be 3. The constraint equation also tells me that x squared plus y squared plus z squared equals 16. Writing it this way, I see that I have 4 equations, and the variables are x, y, z, and lambda. I have 4 equations with 4 variables. Unfortunately, these are nonlinear equations. There's a product of 2 variables in some of the equations. There are squares of things in the other equation, so I can't do something simple like Cramer's rule. Typically, you have to look at this sort of situation on a case-by-case basis. Generally speaking, it's really hard to solve equations like this, but in this particular case, it's not too bad. There are 2 strategies that suggest themselves. Firstly, this equation, and this one all tell me something. They tell me that the lambda can't be 0. Otherwise, if it was, 2 times 0 times a number would not be 1 or 2 or 3. I can solve those first three equations for x, y, and z in terms of lambda, take the result, put it into this equation, and I can figure out what the lambda is. X has to be 1 divided by 2 lambda, y has to be 2 divided by 2 lambda, and z has to be 3 divided by 2 lambda. I don't simplify the formula for y for reasons that will become obvious in a moment. X squared is 1 over 4 lambda squared, y squared is 4 over 4 lambda squared, and z squared is 9 over 4 lambda squared. The constraint equation tells me those three squares have to add up to be 16. If I multiply through by 4 times lambda squared, the algebra becomes very simple. After doing the algebra, it develops that lambda could either be the negative of radical 7 over 32 or radical 7 over 32. There are no other possible values for lambda. For each of these two choices of lambda, we can calculate x, y, and z, and have our candidates for constrained maximums and minimums. For lambda equals negative radical 7 over 32, I got my calculator out and calculated x, which is 1 over 2 lambda, y, which is 2 over 2 lambda, and z, which is 3 over 3 lambda, and got negative 1.069, negative 2.1381, and negative 3.2071 to about 4 or 5 significant figures. The other lambda is the negative of that one. So in these formulas, if I just flip the sign on the lambdas, all it does is flip the sign on the x, y, and z, so I can get the other candidate without having to do any work. The function that I'm trying to maximize and minimize is x plus 2y plus 3z. If I put these values in for x, y, and z, my function value comes up to be negative 14.9665. The function has no constant term in it, so that if I reverse the sign on x, y, and z, it just reverses the sign on the function value. So once again, being lazy, in the second case, the function value is 14.9665. This would be the absolute maximum. That would be the absolute minimum. In the preceding situation, we were looking at function values for our objective function f that lie in a certain surface. If I have two constraint equations that I want to both be true, then I would want to be within the surface described by this equation and also that described by this equation. I would want to be within the intersection of the two surfaces. Typically in three-dimensional space, when you intersect two surfaces, you get some sort of curve. So in three-dimensional space, this problem represents finding the biggest and smallest function values for f that lies on the curve of intersection of these two surfaces. Logic that's similar to what we did before leads us to the differential part of our calculation. The gradient of the objective must be a constant times gradient of g plus another constant times gradient of h. There are now two of these Lagrange multipliers. Also, we have to be within both of the surfaces that we're interested in. As an example of this sort of thing, I'd like to locate the highest spot on the curve in three-dimensional space formed by intersecting the following two surfaces. One of them is x plus 2y plus 3z equals 0. Since this is linear, that surface is a plane. The other surface is x squared plus y squared equals 4. If we were in 2 dimensions, that would be a circle. In 3 dimensions, since this is independent of z, we get a cylindrical surface. So we're going to intersect a plane with a cylinder, get some sort of curve in 3-dimensional space, and I'd like to find out where the highest spot on it. This is going to be my g function. That's going to be my h function. The f needs to be some number that describes to me how high up or below the xy plane I'm located at. The function that I want to make as large as possible has function value f of x, y, and z just equal to the z coordinate. Sometimes people object and say that's not really a function of x, y, and z. If it made a person feel better, they could think of this as being 0 times x plus 0 times y plus 1 times z. The partial derivatives of f with respect to x or y are always going to be 0. I'll have to calculate the gradients of the functions involved. F doesn't depend on x or y, only z. So gradient of f is 0, 0. Partial of z with respect to z is 1. This is my g equation. Partial of g with respect to x is 1, with respect to y is 2, and with respect to z is 3. This is my h function. Partial of h with respect to x is 2 times x. Partial with respect to y is 2 times y, and h doesn't depend on z, so the partial derivative of h with respect to z is 0. Before I write down my other two equations, I'll go ahead and combine the right-hand side into a single vector. Thinking of splitting this up into components, this number and that number must be the same. This number and that number must be the same. And that number and that number must be the same. In addition, my two constraint equations have to be true. Splitting the vector equation up into its components and also writing down the two constraint equations, I see that I now have 5 equations. The variables are x, y, z, lambda, and mu. So 5 equations, 5 variables. As before, these are nonlinear though, so life may be difficult unless the problem has been carefully selected to make it easier. Looking at all of these equations, there's one that I like a whole lot more than any of the other ones, and that would be that one. 3 times lambda needs to be 1. Lambda has to be 1/3. The moment that I know that, I know several other things. 2 times mu times x has to be the negative of lambda, negative 1/3. And 2 times mu times y has to be negative of 2 lambda, negative 2/3. So this will tell me what 2 mu x and 2 mu y are. Depending on exactly what the system of equations looks like, sometimes you can do various bits of trickery, which we're now going to do. These two equations tells me, among other things, that firstly, mu isn't zero. Also, x can't be zero. Also, y can't be zero. So in writing down the equation that I'm about to write down, I don't have to worry about accidentally doing division by zero or anything. So by doing a division, I can figure out that y is 2 times x. I'm going to take this fact and put it into these two equations, and then I'll get two equations that only have two variables in them. X plus 2 times y. 2 times 2x is 4x, plus 3 times z is 0. This equation only has x and z in it, but even better, this equation, x squared plus y squared equals 4, becomes x squared plus the square of y is 2x, equals 4. That equation only has x in it. From this equation, I'll be easily able to figure out the x coordinates of any possible high or low spot. And once I know the x coordinates of such potential candidates, I can use this equation to find the corresponding z coordinate, and z is the thing that I'm trying to maximize or minimize. The x coordinate of any spots that I'm interested in that might be high or low spots are x equals radical 4/5 or x equals negative radical 4/5. But from the first equation, the z coordinates have to be negative 5/3 times whatever the x coordinates are. Putting in the two possible x values, I find out that the candidates for the biggest and smallest z values are z equal that number and z equal that number. This is the biggest z coordinate. This gives me the highest spot. This gives me the lowest spot. For our immediate purposes, this ought to be enough information. I may make a very small follow-on video to this involving an application of these kind of ideas to a physics problem involving the principle of least time. I hope that everybody's having a good day, and I'll talk to you again soon.